Hello everybody. Today I'll be talking about my network science and applications project on economical network analysis based on complex networks. Let us come to the outline of the project. First, the motivation and the definition using complex networks in economical network analysis is introduced. Second, the network representation will be explained using this project. Third, now based on modularity, the network is clustered into different communities. Fourth, the ranking of the stocks based on eigenvector centrality is achieved. Finally, we have the conclusion, references, and the acknowledgement for the project. About the economic network, the motivation is that the variability and the fluctuations of the stock prices are not independent, but are highly dependent and intercoupled with strong correlations with the big business sectors and the industries to which the stocks belong. The usual approach involves the procedure of finding the correlation between each pair of the time series of the stock prices and the subsequent procedure of constructing a network that connects the individual stocks based on the levels of correlation. The factors affecting the stock network include the economic environment, political news, tickers operation, and the investor's strategy. However, the factors can be represented with a correlation matrix. About how we use the correlation to represent this network, in this project, the historical data from January 1st, 2010 to December 31st, 2014 of Nasdaq 100 stock market is used for analysis. Without losing generality, if the close price of the stocks is used and the daily logarithmic profit rate of the stocks is obtained on calculating the correlation, the temporal correlation coefficient between the ith stock and the jth stock can be represented with the equation given in the slide, where the SI is the average profit rate of the stock during the said duration. SI multiplied by Sj is the average of the multiplications of the profit rate of the stock and the stock during the same period, and SI square is the square of the average of the stock profit rate. In this slide, the distribution of the correlation coefficients is presented. It can be seen that most of the correlation coefficients are positive and the peak value is around 0.7. This phenomenon will influence the threshold that will be explained later. In this project, the interest is mainly in the relatively stronger correlation between the stocks. The correlation matrix storing the weight of the stock network is divided into two binary value adjacency matrices representing positive effect network and negative effect network respectively. For positive correlations, when the correlation coefficient is larger than 0.5, the corresponding element in the positive correlation adjacency matrix will be set to 1, otherwise it will be set to 0. For negative correlations, the threshold is minus 0.1. As for clustering, we use modularity to cluster the stocks into communities. Modularity is a measure of the structure of the networks. It was designed to measure the strength of the division of a network into two modules. Networks with a high modularity have dense connections between the nodes within the modules but sparse connections between the nodes in different modules. Through iterative searching for the sub-communities, maximizing the modularity score, the network is clustered into different communities. This is defined by the equation shown in the slide. Now, as we have two matrices representing positive effect and the negative effect network, we have two clustering results. The left side is the positive effect network clustering result. We can see that the stocks are clustered into two communities. In the right-hand network, the network members are clustered into three communities. The connection between them is represented by the lines connecting them. In this project, the eigenvector centrality was used to make a ranking of the stocks. Eigenvector centrality is a measure of the influence of a node in a network. It assigns relative scores to all the nodes in the network based on the concept that connections to high-scoring nodes contribute more to the score of the node in question than equal connections to low-scoring nodes. As eigenvector centrality represents the importance of each node in the network, extracting the top-ranked stocks from the positive effect network and the negative effect network can provide useful information for making trading strategies. Other centrality measures can also be incorporated to generate trading strategies, such as the degree centrality, betweenness centrality, closeness centrality, and so on. In this slide, the 10 stocks with the largest positive effects are represented. We can see that the original point represents the most recent date compared with the starting date. All of the 10 stocks have a better performance than the overall performance of the market. In this slide, the 10 stocks with the largest negative effects are shown. Most of these 10 stocks have a lower or equal or equivalent performance ever since the starting analysis date. Both this figure as well as the figure on the last slide can provide some information to the ambassadors in deciding which stocks should be held and which stocks should be sold out. So the MATLAB code was run and these clustering results were obtained on the command window. The positive relation correlation metrics have been seen to have 2 clusters and the negative ones have 3 clusters. Coming to the conclusion of the project, based on the weighted network generated from the correlation of the stocks from Nasdaq 100 stock market, the stocks are ranked according to the eigenvector centrality and also clustered into several communities. The information given by the ranking is helpful for making trading strategies. The community structure provides a reliable segmentation of the network for possible prediction methods. Since the open price and the trading volume reflect more of the investor's subjective consideration, it is worth studying as a future work. Here we have some references used for the project. Finally, I would like to thank our professor, Dr. Wu, without whom it would not have been able to be possible to grasp the concepts in network science and applications course. We owe him for inspiring us always and making it possible for me to do this project successfully. Thank you.